Geek in a maze. Geek is in a maze of size n by m. Each cell in the maze is made of either dot or hash. An empty cell is represented by dot and an obstacle is represented by hash. Okay, if Geek starts at cell RC, find how many different empty cells he can pass through while avoiding the obstacles. He can move in any of the four directions, but he can move up at most u times and he can move down at most d times. Okay. So this is the first example. We are having a 3 by 3 matrix. We start from 1 0. So it's 0 based indexing. So we have first row, okay, here, second row, first column, and we are having a restriction for upper and down movement. So for upper movement we can only make one upper movement. For down movement we can only make one down movement, and we can make any number of left or right movement, and there is no restriction or limitations for that until and unless we are inside the matrix. Now out of bounds should be encouraged. Yeah, so in that case, like, we have this one, this one, this one, this one, this one, considering, let's check that. Yeah, okay, so this is our so we have a maximum upper moment of 1, maximum down moment of 1. So let's have our matrix dot 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 hash dot hash dot dot, and we are starting from this cell. Okay, so let's say like we are at this cell, and let's change it to 1, indicating like we visited it. Okay, now what are the movements possible? It's given like he can move in any of the four directions. So what are the four directions? The different four directions are upper, down, right, and left, and we have restrictions for this up movement and down movement. We can only make one upper movement, we can only make one lower or down movement. So we can move left, we can move down, we can move right, and we can move up. Right is not possible, it's hash, it's an obstacle. Left is also not possible, it's out of bound. Lower is also not possible, it is a hash, it's an obstacle. Only upper movement is possible. So we reach here. Okay, so we reach here. So after reaching it, we will be changing it to 1. Now what are the different possibilities that we are having? We can move left from here, we can move up, we can move right, we can move down. Down movement is not possible because we are already visited it. Like, it's not an empty cell, we already changed it to 1. Left movement is also not possible, it's out of bound. Upper movement is also not possible, it's also upper bound. So only one movement is possible, it's right. So okay, we move right, and there is no upper or down movement that we make. Here we make an upper movement, so the remaining upper movement will be like minused or will be subtracted to 0 because we made 1. So now we move to right, so we make 1. Down movement is not possible. Up movement, it's out of bound. Down movement is an obstacle. Left movement, here it's 1, we already visited it, and only right movement is possible, and it's a dot. Okay, so we make it as 1. So now what are the different movements? We have one up, we can move up, but it's out of bound, and also we do not have any up movement. That's also a point we can take into consideration. We can move right, but it's out of bound. We can move left, but we have already visited it. So there is only one movement left, that is moving to down. So we also used our remaining limitation, our remaining down movement. So we reached here, we are at 1. So there is only left or right movement possible now. So to the left it's obstacle, to the right it's out of bound. So after doing this traversal, like, we can just take the count of how many are visited. So 1, 2, 3, 4, 5, and that will be our answer. And one of the base condition that we need to check is, like, we need to start from RC. We need to just check whether mat of RC is not an obstacle. because if it is an obstacle, like we cannot move any place. So this must be the base condition that we need to have at the very beginning. Now, what are the values that we are tracking here? Now the values that we are tracking is, what are the current positions, what are our row, what are our column that we are standing, and did we make any upper movement? If we make the upper movement, how many upper movements have we made? Did we make any down movement? And if we make a down movement, how many down movements are made? So we need to hold all these four values. Okay, we need to track all these four values, and for that we can create our own data structure. Let's say it's forable. Okay, it's for us, which holds these four values in order to track these whole values. So four values, and let's say it's forable, and it will be tracking the current row, current column, and how many upper movements is already made. It may be 0 or it may be 1 if we make an upper movement, and it will get incremented every time when we make upper movement till our limit. Okay, so if we reach our limit, we cannot make. So this upper movement will be only if it is not equal to the limit. Okay, if it is not equal to the limit. Same way the down movement is if it is not equal to the limit. Okay, so we will be doing so by looking this structure, like it's kind of a traversal, it's kind of a graph traversal. So this is a breadth first search kind of traversal. We can make use of depth first search also. Let's have a breadth first search traversal, and for that we will be having a queue. So into the queue, initially we will be putting whatever be the value 1, 0, and did we make any upper movements? No. So it's initially will be 0. Any down movement? No. Okay, so this will be in our queue initially. Now we pop this out and look for the different possibilities. Down, okay, down, left, up, right, and only up movement is possible, and it will make us to reach into 0, 0, and we make one up movement, so 1 and 0. Okay, now left, right, from here we have left, we have right, no up movement, it's already consumed or it's out of bound, and down movement, it's not an empty cell, so only right. So we will be popping every time after adding. Okay, so this one only right movement, and it will be to 0, 1, 1, 0. Same way we pop this out, we look for the different directions, and only right will be possible. So 0, we reach to 1, 0. Now we pop this out, we pop this out. Now look for the different possible directions. So we can move down, we can move right, we can move left, we can move up, but only down is possible. So we also made one down move. So we reached 1, 2, 1, 1. Now from here there is a down movement possible, but this down is equal to this limit. This down will be equal to this limit, and we are also checking that we should not make any down movement if it's go beyond our restriction, it goes beyond our limitation. So the idea is simple. We will be just having a data structure to hold all these four values. We will be putting the initial values into the queue data structure, and we'll be doing the general Bfs algorithm. And after that, every time, like if we are able to make the move, we will be changing that cell to 1 to say like we visited it. Okay, and after doing the Bfs, we will be just traversing through this given matrix, which will be updated with ones, and we will be counting this ones, how many ones are present, and that will be our result. Let's do that. So first of all, our base condition, this is very important. So if mat of RC is already an obstacle, we need to return 0. Otherwise we will be doing a Bfs. Okay, we will be passing the initial row, initial column, our maximum number of upper movements, maximum number of down movements, and our matrix. So now we told about our special data structure. So let's call it forble, and that data structure will be holding the row call, the upper count, upper movement count, the lower movement count. Okay, now let's also have a constructor for this. Int row, int call, int upper count, int lower count. Okay, so this dot row equal to row, this dot call equal to call, this dot upper count equal to upper count, this dot lower count equal to lower count. So yeah, so after doing the BFS, what's our next step? We will be just counting the number of ones inside the updated matrix. So for int I is equal to 0, I less than n, I plus plus, where n is the number of row, total number of row, j is equal to 0, j less than m is the total number of column. So if mat of, or the matrix of ij is equal to 1, we need to increase the count of cells, count of possible cells is equal to 0, and this gets incremented, count of possible cells plus plus. We just return this at the very end, count of possible cells. So now our only requirement is to implement this Bfs helper function. So it's not returning anything, so public void Bfs, our starting row, our starting column, our maximum upper movement, our maximum down movement, and our matrix. Okay, so we need a queue which will be holding these 4 values. So for that we made use of the forble data structure, our custom made data structure, and to this we are offering new forble of our starting row, our starting call, and what is the initial starting, the upper count, it will be 0, and down count or lower count will also be 0. Now we also need to make into 1, starting row, starting call equal to 1. So while not q dot is empty, take the current value, forble current is equal to q dot poll. Fine. So what are our different rows calls? Into row will equal to current dot row, into call is equal to current dot call, int current, or let's say upper count. So our upper count of the current cell, okay, the amount of upper movement that we made till now is equal to upper count, and in the lower count, I think, yeah, lower count is equal to current dot lower count. So let's have the left movement. So we can make any number of left movement, we can make any number of right movement, that doesn't affect our upper count and lower count. So if we are moving left, okay, so if y is greater than 0 and mat of row, sorry, y it's called, so mat of row call minus 1 is an empty, we are making it as visited, or the possible cell that we can move. Okay, now we will be offering it new forble of row call minus 1, and no change in upper count, no change in lower count, because we are making a left movement and there is no restrictions for left movement. Same way this happens for the right movement. If call is less than so we can also pass n and m here, that will do good to us. Int m. Okay. Call is less than m minus 1, and then mat of row call plus 1 is equal to a dot. Okay, then we can, it's a possibility, so it's a valid one. So if we can make it as 1 and offer it new for of row call plus 1 upper count lower count. Now we are moving to up, so we are moving up, so we need an extra condition to be checked, that is we need to check whether our upper count is not equal to the maximum number of upper movement u that we can make. So if row is greater than 0 and then our upper count is not equal to u, and then our mat of row minus 1 call is equal to a dot, is equal to a dot. So if all these conditions satisfies, so mat of row minus 1 call will be made as okay, or visited offer of new for of row minus 1 call upper count plus 1, because we made an upper movement, so we need to increment the upper count value and lower count. Okay, now same way down, if row is less than n minus 1 and then down count is not equal to d, and then mat of row plus 1 and call is equal to dot, say mat of row plus 1 call is equal to 1 and q dot offer of new for of row plus 1 call upper count does not change because we made a down movement or lower movement, so our lower count changes. So that's it, this is our BFS algorithm. So the time and space complexity, for time complexity in this BFS algorithm, and the worst case will be visiting all the nodes, or it's will be visiting all the nodes. So the time complexity here will be big of row into column, and here we are already going through all the rows and calls, traversing the whole matrix in order to search for ones, all the possibilities. So it's also causes big of row into column, so big of row into column into big of row into column, which will be the total time complexity will be big of row into column. Now for space complexity, we are making use of this queue, and this queue can also hold the worst case the whole value, so the space complexity will be big of row into column. Now we got a compilation error, upper count lower count. Okay, it's because I missed a parenthesis here. Another compilation, non-static, static is static, yeah, so this has to be static. Because we can only call static methods from another static method. Now I have another one, down count, so it's lower count. So many compile, this has to be like reduced by just again cross checking, but I just straight away gone with the compile and run IDE. So this is a special case where we are starting from 1 2, and 1 2 is hash and obstacle, so that's what we are handling at the as the base condition, at the very first condition. So if such condition arises, we can straight away say 0, because from here like we cannot make any moves, so that's the reason. Let's submit, and it's flying. Yeah. So that's today's problem, Geek in a maze, which can be solved using any graph traversal. I used BFS here.